Okay, let's start, guys. Okay. So good afternoon, everybody, guys. So tomorrow we're gonna start. Yeah. Okay, listen to me. Tomorrow we're gonna start the first lab. Okay. Number one, I have posted the lab description. Okay. What you have to do is that in this lab, there is a link to download a program, the assembler program I told you about. You have to download this program. One more thing I want to tell you about this program for Windows. So if your operating system is Mac, I give you some advice what you have to do. Usually you can do one of two things. You can have dual operating system, or you can have like something like virtual Windows, something like that. Okay, and you can run it after that. Anyway, so try to download it as a program before you come. Again, if you are Windows, you should not have a problem. If you are Mac, you have to do something. If you need help, the team is gonna help you. I will be also in the lab. How can you do it? Okay. Number two, I didn't ask you to buy the board. You actually don't need to buy the board. In the first 5 or 6 labs, you don't need the board actually. Okay, it's enough to use simulator. So okay, so this program has, as I'm gonna explain tomorrow, it has a simulator, so you can use simulator. It should be okay. However, starting from lab 6, I guess 6 or 7. At this time, we are going to distribute the board to you. You are going to need the board, because starting from lab 6 or 7, you are going to start using the input-output devices here. Okay. At this time, simulation is not going to be enough. You need the board. Okay. Also tomorrow, we are going to have a quiz in the beginning. This quiz should cover chapter 1, and as I told you before, all exams, all tests, or quizzes are open book, so you can use the slides, okay? But you can't use electronic devices, so you can bring the slides with you and you can use it. This is same thing for the final, for the tests, for everything, okay? So last time, okay, guys, so last time I explained many things. So let me go spend some time quickly to explain, to see what I did in last time. So last time, guys, I explained, I told you, any computer system should have this architecture. It should have memory, and I explained why we need memory. Memory should store data, and it should store the machine code of your program, and that's what you are going to see tomorrow. So tomorrow you are going to, in the lab, you are going to see the memory. You are going to see all the locations in the memory. You are going to see your data. So when you store, when you know, the good thing what we are doing here, guys, you remember in C language, you used to say integer I, integer J, and that's it. Okay, you don't know where I and J should be locations in the memory, physical location, so that every time you change I, I'm going to change the physical location. Every time I want to read I, I'm going to read the physical location. You are going to see this physical location in this course. So if you have a variable, you can know where it's exactly in the memory. You can go to inside the memory. You can see all the locations in the memory. Also, you will see tomorrow, after you write your program in assembly. Okay, again, don't be panic. I'm not expecting you know any assembly. Okay, so don't worry about that. So you are gonna write it. I want you to see how it is converted to machine code, and how the machine code is going to be stored in memory, as I explained in the lectures here. Okay, so your program actually should be a bunch of ones and zeros, and they should be stored in the memory at different bytes in the memory, as you will see tomorrow. Okay, so also I told you here we have arithmetic logic unit, we have registers. I explained when I work with memory, I told you memory should have locations. Every location has what we call address, and the addresses we have here are 16-bit. Every address is 16-bit, and every location should store only 1 byte. Only 1 byte in a location. You understand what I'm saying? So for example, in location number 1000, okay, in this location, I'm gonna store number 20. Okay, so byte in this location. And again, tomorrow, you are gonna see all the location. You can go to any location and you can see what is stored in this location. I'm not gonna use the word location anymore. Instead, I'm gonna use address. So when I say address, it means the location number. Is that okay? That's why you see here, guys, we have here 16-bit address, okay? And then the data, you can see it's by direction as you see here, because you can write, or you can read. So this is called read, this is called write. You can write or read. Where you can write, you have to tell here for address. Okay, makes sense. Because the memory has too many locations. So if I want to write, you have to tell me where exactly you want to write, in which location. Okay. Also, you can see the data here is 8 bits because every location is storing 1 byte. Okay. Also, I explained last time, and that's what you should fully understand the idea, guys. This is, we have what we call an instruction set. So you should understand what we mean by instruction set. Every company, when they manufacture a microprocessor, they should give you a table like this table. Every company, this table should tell you what instructions the hardware can execute, because all these instructions, these are assembly instructions. Every instruction here is executed by the hardware. Is that okay? Also, they should tell you, for example, this instruction. This is the machine code for this instruction, 1806. Is that okay? And again, because what we're going to do when you write assembly, we're going to write English names this way. And then the assembler, that's what you are going to see tomorrow. So what you are going to do tomorrow, you are going to write English names for instructions, right? And then when you run your program, the program you have that's what we call assembler. This program should convert this one to these numbers and to store them in memory, and you should see them in memory. Is that okay? That's what we call machine code, right? And the idea is why it is 1806, why it's not 7255. Okay, it doesn't matter. Just the way they made it. Okay, when you have this number and you put this number on the hardware is going to do this instruction, right? So this is the people who made it. Like it's the same idea here. The way we designed this one, when I put 00, it's going to do addition. The way I designed it, when I put 01, this way it's going to do subtraction. So this is the way I designed. So you can think this is like a machine code. You got what I'm saying? Anyway, so one more thing. One more thing I explained last time. I explained what we call registers. I told you registers inside the microprocessor. There are some storage units inside the microprocessor, and these registers should help the microprocessor to execute instructions. Okay, so to execute an instruction, I need to borrow storage. Okay, when I get a number, I have to put it somewhere. When I do the addition or multiplication, I have to put the result somewhere. Okay, so I'm not gonna store the program or the data inside the processor because this should be stored in the memory, but they have some storage unit. We call them registers. Okay, last time I explained three important registers. I'm gonna give you more today. One register is called IR. IR means instruction register, and the idea of IR is the idea of the IR is, guys, is when I read, I told you, when I read the machine code instruction, this is how it works. To execute every instruction, it has to go through 2 steps. Fetch, execute. This is for one instruction. Then for next instruction, fetch, execute, fetch, execute. So what fetch means? Very simple. Fetch means I have to read the instruction from memory, right? The machine code, I have to read it. put it in the hardware is going to execute the instruction. So when in order to read it, that's what we call fetch. Is that okay? So, and again, some instructions are 2 bytes, some instructions are 3 bytes, and so on. So I have to read the whole instruction. After that, after I read the instruction, where I'm going to store this instruction, I'm going to store it in IR, instruction register. So there is a register. This register should store the machine code after I read it. Okay. Once I put it here, the hardware is going to do. This is how the processor is designed so that once you have these ones and zeros, so the hardware is going to execute the instruction of this ones and zeros. Okay. This is the first one I explained, IR. The second one, we call it PC, program counter, okay? And the good thing, again, tomorrow, you will see by yourself is a program counter, okay? So the idea, very simple, for the program counter, it's a pointer. I know in the past, many students told me, we learned pointers in C language, but I was not able to understand it. What do you mean by pointer? But in this course, because we are going to use pointer all the time, you will understand the idea of pointer much better. Okay. So let me tell you what pointer means. Very simple. So for example, this is okay, guys. So what I'm saying is that, so what do you mean by pointer? Okay, the way it works is, this is, for example, instruction 1, for example, we're going to start from location 4,000, guys. Okay, we have instruction 2. This one should start from location 1,002, just any arbitrary numbers. Instruction 3 should start from 4,000, for example, 5, and so on. Okay, so in the very beginning, PC should help the processor to keep track, to know which instruction I have to fetch right now, which instruction I have to execute. That's why in the very beginning, PC should point at the first instruction. Is that okay? After I read this instruction, I update PC to point at the next instruction. Okay, so that after I finish this instruction, okay, I'm gonna, what is the next one? PC is gonna help me. PC is gonna keep track. Okay. So in the very beginning, PC here should be 4,000. Okay. And then now microprocessor wanna execute an instruction. So how I'm gonna start? Very simple. I'm gonna ask PC. PC, where are you? Where? So PC is pointing here. So the idea of pointing means PC is storing address for a location. That's what I mean by point. You point. Point means it's storing address. Is that okay? So what happened? I want to execute an instruction right now. I'm gonna ask PC, where are you? I'm here at 4,000. Okay, guys. So I'm gonna read an instruction at this instruction. I'm gonna put it in IR. Then before I execute the instruction, I'm gonna update PC. I'm gonna update it to 4,002. It's gonna point on the next. That's why we say PC always is pointing at the next executed instructions, not the current next one. You got what I'm saying? Because after I read, before I execute this instruction, I update PC, right? So anyway, so once I have the instruction here, I'm gonna execute this instruction. Once I am done, I'm gonna repeat again. I'm gonna ask PC, where are you, PC? I am here. And that's what you are going to see tomorrow. What you are going to see tomorrow, you are going to, once you execute one instruction, PC is going to be updated, right? We execute another one, PC is going to be updated. You got what I'm saying, the idea? This is physical device, hardware, okay? So you will see them tomorrow, PC, program counter. That's why, because addresses we have here are 16 bits, the PC is also 16 bits. Any questions? So this is a register inside the microprocessor. We have other registers. I'm going to elaborate more about more registers, but we have here another register. I started to explain last time. We have what we call flag register. They have a different name. I'm going to explain it later. but we call it flag register. It is a register. This register, every bit is a flag. So this one is a flag, and so on. Okay, so we have different flags. Every bit is a flag. Okay, so what do you mean by flag? Is that a flag? Yeah, something like a flag. Why? Because if this is a 1, it means something. If it is a 0, it means something else. Okay, this is the meaning of it. Okay, so what happened last time, I explained 2 flags. I'm going to explain more today. One flag, we call it 0 flag. We have negative flag. Okay, what you should understand, and that's what you're going to see tomorrow as well, these flags are hardware flags. Okay, so physical devices, hardware. These flags are automatically updated after executing every instruction, automatically. So every time you execute one instruction, flags are updated. You execute another instruction, flags are updated. Why? They are updated to tell you what happened in this instruction. So flags are automatically updated to tell you or to reflect the status of the result or what happened in this instruction. For example, if I do subtraction, that's what I told you last time. For example, guys, if I want to do subtraction, and then after I do subtraction, if the result is 0, the 0 flag should be 1. That means the result is 0. If the 0 flag is 0, that means the result is not 0. Something else, it's not 0. You got what I'm saying? Negative flag, if it is 1, that means the result of the last operation, is negative, right? Otherwise, it is not negative. So one flag, 0 flag to tell you if the result is 0 or not. The other flag should tell you if the result is negative or not. I'm going to give you more flags today, but at least you have 2 flags now. You should understand the concept of flags. Flags, again, are hardware devices, units, okay, register, like flip-flop. Every flag you can think about like a flip-flop. They are updated automatically, and that's what you see tomorrow. Every time you execute one instruction, you are going to see the flags are updated, okay, to reflect what happened. So if the result of the operation is 0, so the flag is going to be updated. 0 flag are going to be updated. So once you execute, so are going to be updated again. So for example, so always they are updated. For example, I did subtraction and the result was 0, so the negative flag was 1. I did another operation and the result was not 0, so now it's going to be 0. So they are updated after every instruction. Is that okay? Also, last time I told you why you use the idea of flags. Actually, as you will understand more in this course, we use flags to help me to do comparison, as you will see later in this course. We used in C language, you used to say something like that. If A is equal to B, you have to do this part, okay? Else, do this part, okay? So this is what you used to do in C language. How the hardware is going to do something like that. As you will see right in this course, guys, as we are going to do in chapter 2, the way you are going to do comparison this way, guys, I have to write 2 instructions, as you will see in this course later in chapter 2. I have to write 2 instructions. Number 1, I have to do subtraction. Subtraction doesn't make any sense. I'm not interested in the difference. Why you do subtraction? Okay, I'm not doing subtraction because I want to subtract. I want to do subtraction just for comparison. How? I'm going to tell you what. So for example, I'm going to do subtraction. Okay, and then once I do subtraction, automatically flags are updated. That means now if the 0 flag is 1, that means they are equal. Otherwise, if the 0 flag is 0, that means they are not equal. Is that okay? Next instruction, we call it branch instruction. I'm going to teach later, we call it branch instruction. This instruction is going to branch, for example, if this condition is false, you have to branch to here, if A does not equal B, right? So here, the branch instruction is going to branch to else, if the 0 flag is 0. So again, I'm going to use one instruction just to update the flags or to set the flags, set the flags based on the value or based on the result of the comparison. Then I'm going to use another instruction. This instruction is going to just jump or not. It's going to jump or not based on the value of the flex. So this one is gonna just use the value of the flex you already set. That's why you need to set the value first before I use it here. Is that okay? Anyway, so you'll understand this better later, but this is how it is done by the hardware. Okay. That's why we need flex. This is one of the. There is another reason for flex. I'm gonna explain today, but at least for now, when I do subtraction, I can do comparison. I can know if they are equal or not. I can know if it's greater or less as well. Okay, by flex. Okay, and these flex are updated automatically. Okay. What I'm going to explain right now, guys, I think let me go through. I think I explained everything. Yeah. Okay. What I'm gonna explain now is okay. Let me complete. Yeah. What I explain, I want you to understand, guys, what is the difference between microprocessor and microcontroller? What is the difference between them? Is that okay? So I'm gonna tell you the difference now. Okay, guys. As I told you last time, guys, microprocessor alone cannot make a computer, cannot make a system, right? As I told you last time, microprocessor is a part of the system, as I told you. So last time I told you we need to have like microprocessor, and then you should have memory, you should have input-output devices, and then you should have buses to connect everything together. All of this, I can say this is a computer system. This is a computer system. Is that okay, guys? Okay, so the difference is that microprocessor alone cannot create a system, cannot create a computer system. Okay, it needs help from input-output devices. They have to work together to create a system. Okay, however, if I put everything together in one chip, by the way, if you open your laptop today, you will see every unit separate. So you will see memory. You can see the memory chip separate. You can see the processor separate. They are separate, right? However, okay, if you put everything on one chip, that's what we call microcomputer. That's what we call microcontroller. So everything here is going to be on one chip. Okay, that means this chip, can you see this? This is a microcontroller. So this is a computer system. That's true. This is a computer system, right? So inside this chip, there are memory. It has memory. It has circuits for input-output. It should have microprocessor. It has other things I'm going to explain later. For example, so inside this chip, guys, there is a circuit for serial communication. This is something I'm going to teach later. Serial communication. There is some circuit to do like timer system. There is one circuit for analog to digital converter. We have some circuit for pulse width modulation and other subsystems here. All of them are on one chip. Okay, guys, any questions? So this is microcontroller. So microcontroller, guys, it's a one chip. This chip, it has inside, it has microprocessor, it has memory, it has other devices. So this is a system by itself. It is a system. Okay, and as you will understand also today, guys. So this is a computer. However, this computer, it doesn't have too much resources like your laptop, right? I told you last time. So here we have 24 megahertz frequency. Your laptop has up greater than 2 gigahertz, right? So 24. This is not a bad thing, by the way, because 24 megahertz should be enough. It depends on what you are going to do with this chip. I'm not going to run MATLAB using this chip. You got what I'm saying? This chip, I'm going to use it like for a traffic signal to make like the traffic signal to run the traffic signal. Okay, or I'm going to use it in a microwave, or I'm going to use it in GPS. Or so it's going to be similar. So that's what I'm excited. So here it's going to come again. So now, any question about the difference between microcontroller and microcontroller? I think that's easy because microcontroller is just one chip. This chip has a complete system. Okay. Now, microcontrollers are used to make what we call embedded systems. Microcontrollers are used to make embedded systems. So what do you mean by embedded system? Embedded system is a computer system, but this computer system is not general purpose. Your laptop is general purpose. Why general? Because I can run MATLAB, I can run songs, I can run different programs, right? General, right? However, this microcontroller is a computer system, but it has a dedicated function. In all its lifetime, it's going to do only one task. You know what I'm saying? For example, your camera, if your camera has a microcontroller, okay, so in all its lifetime, it's going to do only one task: GPS, routers, a microwave, all so MP3 players. Okay, so all of these in digital watch. So, for example, if I use this one for microwave, so in all its lifetime, it's going to run only one program. Okay, by the way, this program we call it firmware. Maybe you already have heard the word firmware. Okay? Okay, so that's the meaning of embedded system. Okay, so yes.
No embedded systems run on memory.
Sorry, say that again.
I don't understand why the firmware is stored on read-only memory chips.
Why firmware is stored?
Why is firmware run on read-only memory chips instead of memory chips that you can write on?
Okay. Yes. Okay. Because look here. Let's agree on this. So every embedded system, okay, as I'm going to explain later, we have two types of memory. We have what we call volatile memory, and we have non-volatile memory. Okay, maybe you're already familiar with these two terms, right? Volatile means once you turn the power off, whatever in the memory is going to be gone. Is that okay? Okay. We also have another type we call non-volatile memory, like your flash memory. The flash memory or the memory stick, whatever you call it, the flash memory is non-volatile. Okay. So once you turn if it is not connected, you still have the information, right? That's why I think this is a question in the assignment. I'm asking you why every embedded system should have non-volatile memory. You understand what I'm saying? So that's a question. Why every embedded system should have, for sure, you still have volatile, but still you should have non-volatile memory. The reason I should have non-volatile memory to store the firmware there. You understand what I'm saying? So that if you disconnect the power from the camera, or if you disconnect the power from the MP3 player, still the program is there. You're not going to lose the program. You get what I'm saying? That's why it has to be in read-only. Again, maybe I'm not using the best word. I don't mean exactly read-only. I mean it has to be non-volatile. That's what I mean. Maybe it's not very accurate. You get what I'm saying? Because what actually to do from time to time we update the firmware. From time to time we update the firmware. You get what I'm saying? So anyway, maybe you're right. I'm not. Maybe this is not very accurate. I mean here non-volatile memory. Okay, guys. Okay. So now I'm gonna come to an important point, guys. Okay. So these magic chips, to me, they are magic chips to me. Okay, and they are making a revolution in our quality of our life. Okay, that's for sure. Why you call it magic chip? Okay, I call it magic chip because it's a computer system. It's a computer. This is a computer. Who can imagine I can make a computer in a small chip like this one? It's a computer. This computer, if you connect to sensors, if you put a program, you can make a lot of very smart things, right? That is why I have several examples here to better understand what I'm saying. So number one, how we can use this chip? This chip are used everywhere in our life, everywhere. Okay, our cars. I read that in some cars there are maybe more than 100 chips like this one, and you know now the prices of the cars are too high because we have a problem in these chips. Okay, it's these chips, and now we have a problem. They are expensive. There is a shortage. There is a shortage of these chips. That's why the prices are high. Anyway, so these chips are everywhere to make everything around us smart. Okay, you know now We have smart power grid. We are talking about smart cars. Everything we need to make it smart. How can we make it smart? Anything in our life, how can we make it smart? Very simple. The way we are going to make it smart, if you have sensing, if you sense, and you have computation, sensing, computation, you can make it smart, right? So program, you do sensing, and then you have a program, okay, to execute a program, you can make anything smart, okay? So that's why these chips are used everywhere, and in the future, we are going to have more of them. Some of these chips are already connected to the internet. They can, like you can make what we call IoT device. For sure, I'm quite sure you are familiar with IoT, Internet of Things devices, a small device. This device has chips like this one. Okay, they are connected to the internet. They are computers. Okay, they are computers. So I just want you to understand the idea how these small chips are gonna make things smarter. That's why I'm gonna run 2 videos now. Okay, like what we call a smart spoon. So I want you to understand what I mean by smart spoon. How a spoon can be smart. Okay, and how what this means and how. Okay, let's see if this one is gonna work.
Basic act of getting food from plate to mouth can be Parkinson's disease, a disorder of the central nervous system. Simply eating a meal can be an ordeal. The most common symptoms of the disease are related to movement. The basic act of getting food from plate to mouth can be difficult and frustrating. But now there might be a solution. Lift Labs, based in San Francisco, California, has developed a small device that tracks and compensates for small vibrations and tremors. Anupam Patak, the founder and CEO, explains that the technology behind liftware is similar to the image stabilization feature in high-end cameras.
So yeah, so track and compensate. Track and compensate. You are gonna track by sensing. So you are gonna sense. For example, if the spoon is this way, if I sense the spoon is this way, okay, this is sensing. Now I'm gonna compensate by running a program. So I have a program. The program is gonna say, yeah, you are this way, so you have to compensate this way. That's what exactly I said. So as he's gonna say right now, inside this spoon, there is a chip, microcontroller chip like this one to make it smart. Again, it's smart because you run a computer program. That's how we call it smart, right? You sense, your computation, you can make things looks smart, but it's better for sure than.
He spoke to VOA via Skype.
So what we've done is taken that same concept and applied it to a handheld device that would help people with a lot larger jitters. So somebody with a neurological disorder might be moving, up to an inch in magnitude. There's a little computer inside that's running an algorithm that would.
Little computer. He means microcontroller running algorithm program. Okay?
Basically, sense the person's motion, determine whether that was intentional or unintended. And if it's unintended, move opposite to what that motion does.
The result is that the device remains smooth and level despite the movement of the user's arm or hand. Food that would normally fly off remains on the spoon.
That just makes all the difference. I'm telling you.
Being able to see somebody eat, on their own for the first time, or even just eat better, has made it's a hugely impactful thing.
The device costs $295.
Anyway, I have another example here. Just I want you to understand. So this chip can be in the traffic signal as well to sense if there are cars, and then it can control the light. Okay, it can be it can do anything you can think about. You can make it better. So let's look at this one, baby bottle. So how this can be smart. Not working. Anyway, so I think I put it in the course website. Okay, guys. I think you understand the concept now. Any questions? Great. So now I'm gonna focus more on our microcontroller here. So our microcontroller, I'm gonna tell you more about this one. So our microcontroller is 16-bit CPU. So what do you mean by 16-bit CPU? That means you can do operation on 16-bit data. Okay, as you will see later in this course, I can add 16-bit plus 16-bit. I can multiply 16-bit by 16-bit. I can compare 16-bit by 16-bit. Okay, the maximum operating frequency is 25, but we're going to use 24 megahertz. Okay, inside the chip, on a chip, inside the chip itself, it has RAM inside the chip. This is volatile. So that means everything is going to be gone once you turn the power off. So this is the number of our microcontroller, by the way. So we have up to 12 kilobyte inside here, inside this chip. Also inside this chip we have EEPROM. Also we have flash memory inside this one. Okay, so as we are going to do in this course, as you will see by yourself in this course, what we are going to do, my program, I'm going to store it in the flash memory, so that even if you disconnect the port, your program is going to be still there. Okay. Also, I told you inside this chip there are too many things inside this chip. So inside the chip itself there are too many things. Like we have serial communication circuit, we have timer circuit, we have pulse width modulation, we have analog to digital. There are many circuits here inside this chip. That's why I'm saying it's a complex system. It's a magic chip. It has CPU, it has memory, it has you can do a lot of things using this small chip, and it's not expensive, by the way. As far as I know, maybe $10, I guess, $10-12, something like that. Anyway. So look here. So everything here is just a connection. So if this board, if you see this board, guys, all what's happening in this board is just to connect the device to the pins here. That's it. So there is nothing else here. So everything inside this chip here. Okay. All the board just to connect wire is the input-output device to the pins here. Okay? Now, I told you we have static RAM. This static RAM is volatile. Also, we have non-volatile, which is flash memory. Okay. Now I want to talk about registers. What kind of registers we have here, and then I'm going to talk about two more flags. I already explained two flags. I'm going to explain two more. The registers we have here, guys. We have a register. We call it, as you see here, register A, which is 8-bit. We don't have, as I told you before, usually we don't have too many registers. I don't need too many registers. You got what I'm saying? It's because register just is going to help to execute an instruction, right? But for memory, yes, we need too many locations in memory. It's completely different. Okay. So here we have a register. We call it register A, as you see here. This register A is a byte. Register A is a. We have only two registers that are bytes, A and B. So we have register A, it's a byte. We have register B, it's a byte. And tomorrow you are going to see register A and register B. So every time you execute an instruction, you are going to see what is the value of A and what is the value of B. So these two registers are inside the microcontroller, register A and register B. Okay. Every one of them is a byte, storing byte. Is that okay? One more thing you can do, guys. I can concatenate A and B together. Concatenate A and B to create what we call register D. You understand what I mean by concatenate? So here, concatenate. So register D is not a new register. I used one register 8 bits and one register 8 bits. I concatenate them to create a register which is 16 bits. You got what I'm saying? That's why I want you to I want to make sure you understand this fact. That's why I'm gonna ask you in the quiz. I want to make sure you understand that this is concatenation. Okay. So for example, I'm gonna ask you something like this one. Okay. So for example, guys, if register A is storing F2, if register B is storing 37, okay, guys, the register A is storing a byte. I can use A as a byte, as you will see later in this course. I can use register B as a byte. Is that okay? Or I can concatenate them to use a 16-bit register. That's why, and the way you concatenate it, guys, B first and A, for example. And that's what I'm gonna ask you tomorrow in the quiz. Okay. For example, if I'm gonna give you register A, register A has this value, register B has this value. What is the value stored in register D? Okay. Actually, register D is just concatenation from B and A. B should come first, or B should be the least significant byte. A should be the most significant byte. That means B register D should store F2 3 separate. Is that okay? So if you need 2 bytes, you have 2 bytes, A and B. If you need a word, you can concatenate A and B together, and that's what we call register G. Is that okay? I can do the opposite. So tomorrow, for example, tomorrow I can tell you, for example, register D is storing F or A to B3, something like that. Okay, this is register D. Then I'm going to ask you, what is the value of register B and what is the value of register A? For sure, the first byte here is B. The most significant byte is A. Also, that's what you are going to see in the left tomorrow. So you're going to see in the left tomorrow, you are going to see A, you're going to see B, you're going to see D. So you will see that register D is just a concatenation of A and B. Is that okay? Any questions? I think it should be easy tomorrow if I give you register D and ask you what is the value of A and B. Also should be easy if you give you A and B and ask you what is the value of register D. Is that okay? Okay. So A and B, each one of them is a byte, or we can concatenate to create register X and D, which is 16 bits. Is that okay? What other registers do we have? We have register X with 16 bits. We have register Y, which is 16 bits. Is that okay? We have PC, which is 16 bit. I would explain what is PC, right? We have another one, another register we call SP. SP, stack pointer, okay? This stack pointer, this one is going to be used to point at the top of the stack, right? I'm going to leave this one later because later I'm going to teach what is stack. What do you mean by stack? And later you are going to understand a stack pointer SP has a dedicated function like PC. So it's not general. You cannot use it in your program because it has a dedicated function like PC, right? So now what you can use in your program, you can use register A, you can use register B, you can use register D, or you can use X and Y. That's all the registers we have. On top of that, we have 2 more registers, but this is not general purpose. This is not for your use. They have a dedicated function like PC. PC should be used to point at the next executed instruction, and that's what we'll see tomorrow, right? A stack pointer should point at stack. So later I'm going to explain what is a stack. So it's the same idea like PC. It should point, should store address, okay? But this one should store point at the stack. So later I'm going to explain what I mean by stack. This one should store the next executed instruction. Is that okay? I think it's assignment, and tomorrow I guess in the quiz. Also, I'm going to ask you, what is the value stored in PC? So PC should store the next executed instruction. Okay, the address. Sorry, PC should store the address because it's a pointer, and the idea of any pointer, okay, should store address, right? So that's why it point. When I say point, just to understand better what I mean by point means storing address. That's why you point, okay? Because storing address. So PC is not storing instruction. It's storing the address of the next executed instruction. And the instruction itself is stored in memory, okay? So anyway, now we have another register. We call it flag register, or it has another name. So we have here, yeah, this one. Okay, guys. So we have one here. We call it. This one is called a condition code register, or sometimes we call it CCR, condition code register, or that's what we call it flag register, whatever you want to call it. Usually we call it flag register because this register has all the flags we have. Every bit is a flag in this register. Is that okay? So we put all the flags together in one register. This register is called CCR or flag register. Okay. So here, for now, I'm gonna focus only on these four flags. Later in this course, we're gonna use I flag. So we have flags here. Let's first focus on these four flags, right? I already explained two flags from them. We have here what we call zero flag. Also here we have what we call negative flag. And I told you what it means, right? What zero means, what negative flag means. These flags are updated automatically after executing every instruction. Is that okay, guys? So what happens is that we have two flags. One is negative for negative flag and zero flag. These two flags are used for comparison, as I explained before. If you want to do comparison, if you want to compare, is that okay? We have two more flags I'm going to explain right now. These two flags are used, the first two here. These two flags, C and V. C means carry, V means overflow. So these two flags are used to know if there is overflow or not. Again, so we have two flags for comparison. Flag N is negative and zero flag. We have two more flags are used for overflow to know if there is overflow or not. So what do you mean by overflow? Okay, I'm going to tell you. Any questions? Okay. Now let's explain what do you mean by overflow. Okay. It's come here. First, okay, you are telling us you are going to explain two flags, right? These two flags are used in order to know if there is overflow or not. Is that okay? Yes. So what do you mean by overflow? What overflow means? I'm going to tell you what I mean by overflow. First, let's look at the English name, overflow. What overflow means in English? Overflow, right? Overflow simply exceeds the limit. Two words, exceed the limit, right? If you exceed the limit, at this moment we say there is overflow. You exceed the limit. That's what I'm saying. That's exactly what I mean. So overflow means you are exceeding the limit. Yeah. So what limit? What do you mean? Okay, I'm gonna tell you what I mean. Look here, guys. If I do this operation, if I write instruction to do this operation, I want to add 1 byte. For example, I want to add register A to register B. I want to add byte plus byte, and then I want to store the result in a byte. Is that okay? So here I'm going to write instruction. In this instruction, I'm going to add byte plus byte, and then I want to store the result in a byte. Is that okay? What it means that overflow can happen in this operation. What it means? It means, think about it. As I explained before, every byte should have a limit. How big the number you can store in a byte? You remember? In case of unsigned, in case of byte, you can store a number from 0 to 255. This is a limit. This is the limit you are going to exceed, right? So byte can store a number from 0 until 255. Is that okay? If this is unsigned. In case of signed, as I explained before, it can be from negative 128 until 127. This is the limit. Is that okay, guys? Is that okay? So again, there is a limit on the number I can store in a byte. Makes sense, as I explained before. Is that okay? Now, what do you mean by overflow? I'm going to tell you what I mean by overflow. When I add a number plus a number, maybe the result is going to get bigger, right? Maybe the result is not going to be enough to store in a byte. You got what I'm saying? For example, I can put here 200. Okay, 200 can be stored in a byte. That's totally fine because you can store up to 255. So this one can store 200. Here I can put 200, which is fine. However, when I add them together and I want to store the result in a byte, okay? Overflow is going to happen. Overflow means you want to store the result in a byte, but actually byte is not enough. You exceeded the limit, right? Because 200 plus 200 here, I need a space for 400. I need a space for 400. Is that okay? That's the meaning of overflow. So overflow. So if you do addition, and then you find there is overflow, that means the result you are gonna get here is wrong. This is not the correct result because I don't have enough space. Okay, that means there is something wrong in this operation and you have to fix it. You understand what I'm saying? That's the meaning of overflow. You understand what I'm saying? So again, guys, overflow means overflow can, even if you want to store word plus word, overflow also can happen because word also has a limit. If you exceed the limit, overflow is going to happen. You got what I'm saying? Any questions? Okay, there's a question. I think I asked in the assignment why overflow cannot happen if these two numbers have opposite sign. I need someone to answer. You got what I'm saying? So if these two numbers have opposite sign, one is positive, the other one is negative. In this case, it's impossible that overflow is not going to happen. You understand what I'm saying? Any answer? Yes. So what you want to say, I have a number, and then I'm going to get this number smaller, right? So it's not going to exceed the limit because it's going to be smaller, right? Usually overflow is going to happen when these two numbers assist each other. That means both of them have the same sign, positive, positive, negative, negative, unsigned, unsigned. You understand what I'm saying? So anyway, so now you did addition. Listen to me. I did addition. And then I want to know if there is overflow happened or not. Who's going to help you? Two flags. We have one flag. We have what we call carry flag. And also we have overflow flag. V flag, and C flag. What is the difference between them, between C and V? I'm going to tell you. The C flag is going to be 1 if there is unsigned overflow. V flag is going to be 1 if there is signed overflow. Let me say it again. Very simple, very simple. Let me say it again. Number 1, you should understand what I mean by overflow. Overflow means you want to add two numbers, but you didn't give me enough space. That's why the number you are going to get is a wrong number. It's not true, right? Because you want me to store 400 in a byte and I don't have enough space. That's why you are going to get a wrong number. I'm going to give you more example to understand it, okay? And now, after I do the addition, I want to check if there is overflow or not. If there is no overflow, that means the result I got is correct result, right? There is no overflow, it's okay, right? But if there is overflow, that means it's wrong result. So my question is, how I can know? Very simple. If your numbers are unsigned, who's gonna tell you? Carry flag is gonna tell you. If your numbers are signed, who's gonna tell you? V flag, overflow flag is gonna tell you. Okay, guys, let me say it again. So if you do addition, and you know that your numbers are unsigned, the numbers are unsigned. So should you check the C flag or B flag? I have to check the C flag. I should not care about the B flag. Okay, in your program, you have to check the C flag because the numbers are unsigned. If your numbers are signed, right? So which one I have to check? I have to look at the V flag, not the C flag. I know most of the students are confused here. Please listen to me. I know many students are confused here. Okay. Computer does not know if the number are signed or unsigned. That is why the computer is going to give you the two answers, C and V. Okay. So when calculating C, the computer will consider your number unsigned. When calculating V, the computer is going to consider your number unsigned. Signed and unsigned. Okay, because it doesn't know. Who should know? You are the programmer. You should know. In your program, you have to check either C or V. You understand what I'm saying? Based on your number signed or unsigned. Listen to me. I know many students are confused here. So you're asking me, number signed or unsigned? Okay, so computers is going to give you the two answers. If your numbers are unsigned, you have overflow, or you don't have overflow. If your numbers are signed, you have overflow, or you don't have overflow, right? And then you, as a programmer in your program, are you going to check C or V, right? You understand what I'm saying? So that's why you are going to get the two, both of them. Even if your number are unsigned, you will get V, right? You understand what I'm saying? Computer doesn't know, okay? You are the one who knows. That's why it's going to give you the two answers. Okay? So now you understand what I mean by overflow. Now you should understand if you do addition and you wanna check if there is overflow or not, which flag you have to check, carry flag or overflow flag, okay? But now, please tell me why we have two different overflows. Why it's not one for both signed or unsigned? Why it's two separate cases? Or let me say it in a different way. Maybe, as you will see now in some cases, maybe I have unsigned overflow, but I don't have signed overflow. Maybe I have signed, but I don't have unsigned. Maybe I have both. Maybe I don't have any one of them. You get what I'm saying? Why? Why these are two different cases? Simply because the limit is different. Because if you go back here, in case of unsigned, the limit up to 255. But here the limit is to 127, negative 128, because the limit is different. That's why these are two different things. Okay, maybe if your number unsigned, you don't have overflow. But if the same numbers, you consider them signed, you have overflow, right? Or the opposite, right? Because this limit is different. I'm going to give you examples now. I have in this slide, I have examples. I intentionally selected this example so that in one case, you have signed overflow, you don't have unsigned. You have signed, you don't have unsigned, or you have unsigned. I just want to tell you, if you have one of them, it doesn't mean the other one should exist or not. There is no relation, they are separate. You got what I'm saying? So if you have unsigned, it doesn't mean you have signed or you don't have signed. No, there is no relation. Okay? Anyway, yeah, separate, because the limit is different. Any questions? Okay, now, so now guys, you should understand what is the meaning of overflow. How can you catch the overflow? How can you know if it's overflow or not, right? How can you know? And why you have to know? You have to know because the result you are going to get is false. It's not correct result. Because I'm going to store the result in a byte, but I need more space. That's why you are going to get a wrong result, as you will see right now, right? That is why, and how can you solve the overflow problem? I'm going to tell you later how can you do it. So if there is overflow, if I add byte plus byte, and we have overflow, right? So what can I do? All what you have to do, you have so byte is not enough. So you have to add word plus word, not byte plus one, because word is going to be bigger space. You need bigger space. You get what I'm saying? So instead of adding byte plus byte, okay, so your numbers are big than what you think, or bigger than what you expect. That's why you had overflow. So you can have word plus word, okay? Because word plus word you are going to have. Now, look here, guys. Two separate things here. I want you to understand two separate things. The first thing is computer is going to give you C flag, carry flag, and overflow flag. Both of them are going to give it to you, right? And that's what you are going to see tomorrow. So I'm going to see tomorrow all the flags are updated after every instruction are updated. You are going to see the zero flag, negative flag are updated. Also, the two overflow flags are updated. Is that okay? So this is automatic. You don't need to do anything. So after you execute every instruction, the flags are updated. That's what you'll see tomorrow. Is that okay? This is one thing. Other thing is, the other thing, and also that's what I'm going to ask you tomorrow in the assignment. What? Tomorrow in the assignment, and also, tomorrow in the quiz, and also this is a question in the assignment. I'm going to give you two numbers. I'm going to ask you, if you add these two numbers, what are the values of the flags? Okay, so this is test tube, not computer. Computer is going to do it automatically. Okay, so I'm asking you, what will be the values of the flag in the computer? Okay, you understand what I'm saying? So I'm going to give you numbers. I'm going to ask you what are the values of the flag. So let's do it. Okay. Number one, you will see right now I have too many examples to understand better. Okay, guys, you have two numbers. You have two numbers. Okay, this is 1 0 1 0 whatever 1 0, and have another number here 1 0 1 0 whatever. Okay, guys, you add this number bit by bit. You add this number bit by bit, and then you have a result. You have a result here. Is that okay, guys? Now, zero flag. Can you know if the computer is going to do this operation, what should be the zero flag? Very simple. I'm going to look at the result. If the result is 0, 0 means 0, 0, 0, 0, 0. All the bits are 0. So the zero flag has to be 1. Very simple. Okay? That will be a question. It's a question. I'm going to give you examples now. Okay? I'm going to give you two numbers, and then I'm going to ask you what will, if you add these two numbers by the computer, what will be the values of the flags? So number one, zero flag is easy. All what you have to do normal addition, bit by bit addition. And then look at the result. If the result is 0, so the zero flag has to be 1. Otherwise, it is 0. That's easy case. Okay. Now, look at the negative flag. For the negative flag, you have to look at the most significant bit. Okay. If the most significant bit 1, that means the result is negative. So the negative flag has to be 1. If this one is 0, so this one should be 0. I'm going to make it easier. I'm going to make it easy. You just copy the most significant bit, put it here. You just copy the most significant bit. So that if the most copy the most significant bit is 1, negative flag should be 1. If the most significant bit is 0, so this one is 0. Is that okay? So again, let me be clear. Tomorrow I'm going to give you two numbers. I'm going to ask you to add these two numbers and then give me the values of the flags. Okay. So these are two easy cases. Let's have to. What about now? What about the carry flag? What about the V flag? Okay, guys, look at the carry flag. Very simple. Carry flag, guys, when you add two numbers, if there is a carry this way, so this will be the carry flag. So you know when you do addition, I'm going to give you example now, but if you do addition, if there is a carry, if the carry is 1, so this is the carry. That's why it's called the carry. If the carry is 0, so this one is 0. Okay, this is the carry. And this carry, actually, this carry means unsigned overflow. Why? Because this carry, that means I need bigger space. When there is a 1, think about it. When there is a 1, that means I need bigger space. You got what I'm saying? So again, so the carry flag should equal to the carry. If you do addition, if there is a carry, this carry is gonna go to the carry flag, and the carry flag is gonna tell you if there is unsigned overflow or not. Right? Now, let's come to the last one. How can I do the overflow flag? Okay. Before I'm gonna give you example. Don't worry, but let me finish. Again, I'm gonna tell you a very simple rule. Very simple rule about the overflow flag. Look at this one, you guys. Very simple. If I add positive number plus positive number and I get negative number. Okay, look here, let me say it this way, guys. The V flag, again, the V flag should tell you if there is signed overflow or not. Signed overflow. The V flag is always 0, except in 2 cases. It is 1 in only 2 cases. The overflow flag is 1 just in 2 cases. If I add a positive number plus positive number, I get negative number. That means if this number has 0 at the end here, 0, and then I got 1. In this case, overflow flag should be 1. The second case, I add negative flag plus negative flag, and then I got a positive flag. Sorry, I add negative number plus negative number, and I got a positive number, something like that. So if you look here, guys, if you find these two have the same sign, either 0, 0, or 1, 1, and this one has a different sign, that means there is overflow flag. I'm gonna give you more example to understand it better. But tell me what you are saying. How I add positive number to positive number, I get negative number, add negative number to negative number, get positive. That doesn't make sense. You agree? Yes, it doesn't make sense. That's true. That's why you have overflow. Okay. The reason, because I got a wrong result. I added positive, but also I got negative. I got negative because it's a wrong result because of the overflow. You understand what I'm saying? I added negative plus 8, I got positive because it's a wrong result, as you can see right now, because of the overflow. Okay. Let me give you example. I think the best way to understand this one is examples. Okay. So because I'm gonna ask about this one tomorrow, it's already on the assignment. So I have too many examples. Let me go through these examples here. Okay. I'm gonna solve this example with you one by one. Okay. Okay. Look here, guys. I'm gonna hide the result here. Okay. So let's have these two numbers, guys. Okay. 1 plus 1 0 0. Let's do the addition. 1 plus 1 is 0, and then we have 1 here. 1 plus 1 is 0, and we have 1. 1 plus 1 0 0 0, and then we have 1 here as well. So this is normally binary addition. 1 plus 1 is 0, 1 plus 1, and then we have 1 here. We have carry here at the end, which is this one. Okay, guys, look here. Most of the students are confused here. This carry is not the result. Here I'm adding a byte plus byte, and this is the result. You have to look at this carry is not a part of the result, just a carry, right? So here I'm gonna add byte plus byte, and this is the result. Is that okay? So now let's see. That's what I'm gonna happen tomorrow. Okay, I'm gonna give you these numbers. I'm gonna give you two numbers. Then I'm gonna ask you about if the computer is gonna do this addition, what are the values of the flags? Okay, so let's start one by one. Zero flag. What should be the value of the zero flag if you do this addition? 1 should be 1. Why? Because the result is 0. This is not a part of the result. Carry is not a part. I'm adding byte plus byte, and then I'm gonna want to store the result in a byte. Okay. So anyway, this is number 1. Number 2. What about the negative flag? This is the result here. 0, because the result is not negative. It's supposed, as you see here, it is not negative. Or very simple, just copy this bit. Copy this bit here. That's it. Okay. Now let's look at the carry flag. Is there a carry? Yes, the carry result. So the carry flag should be 1. Is that okay? Now let's look at the V flag, overflow flag. Overflow flag should be 1 or 0. Look, this case, don't think about it. In this case, you don't need to think about it. It's 0. Why? Because the two numbers have different sign. This is a negative number. This is a positive number. Don't think about it. If overflow, it's impossible to happen here because the two numbers have different sign. So don't. This is the case you don't think about different sign. So overflow will never happen. So that means it is 0. Is that okay, guys? So now, what it means when the carry is equal to 1? What it means we have unsigned overflow. What it means that the V is equal to 0. It means we have signed overflow. What that means? It means if these numbers are signed, you have correct answer. If these numbers are unsigned, the answer is not correct. Let's see. So what I'm gonna do now, guys, look here. I'm gonna consider this number signed. So this one is -1 plus +1. I got 0. Okay, which is correct. +1 plus -1 is 0. So I don't have overflow, signed overflow. Is that okay, guys? So it's correct. Now let's look at if they are unsigned. Okay, in case of unsigned, this number is 255. This one 255 plus 1. I got 0. Actually, the correct answer should be 256. But 256 exceeded the limit because my limit is 255. That's why I got wrong answer. I got 0. 255 plus 1, I got 0, right? Because it's wrong. Okay, guys? By the way, I'm gonna ask you tomorrow, is there signed or unsigned overflow, right? The easy way to do it, I'm gonna say the easy way and the difficult way. because some students did the difficult way. The easy way is, I told you, I'm going to look at the carry. If there is a carry, so there should be unsigned overflow. Then I'm going to look at the V. If it is 0 or if it is 1, that means there is signed overflow. This is an easy way. What happened, some students did it in a difficult way. What they did, they converted this number, they did the calculation as I did here. And if the result is correct, so there is no overflow. That's true, but it's just more difficult. You get what I'm saying? So here, the result is correct, so I don't have overflow here. Here, the result is not correct, so I have overflow here. Is that okay, guys? Let's have more examples. So for example, let's look at this example, okay? I want to add these two numbers together. So again, this is just binary addition. 0 plus 1 is 1, 1 plus 0, whatever. So just add bit by bit. So it's very easy, right? So add bit by bit. There is no carry here. At the end, there was no carry here. Is that okay? Now let's talk about one by one. What about the 0 flag? 0 flag. This is the result is here. Again, the carry is not a part of the result. This is the carry. What's the 0 flag? 0. There is no, the result is not 0. Let's look at negative flag. It is 1 because the result is negative. Is that okay? Let's look at the carry. Is there a carry? No, there was no carry. Now let's look at the V flag. You don't need even to think about it. This is a negative number. This is a positive number. So you don't even need to think about it, okay? So it should be 0. That means if your number signed or unsigned, you have a correct answer, right? Because there is no overflow in both cases. That's why if you do the calculation, you will find the answer is correct. So when I did the calculation in case of signed number, this one was negative 86, this one is 85, and got my negative 1, which is correct. In case of unsigned, this is 170, and this is 85, I got 255, which is correct. Okay, guys? Any questions? I know students are going to be confused because about signed or unsigned. Keep in mind, computer doesn't know. Maybe this number unsigned. Maybe this number unsigned. However, when the computer is going to calculate the negative number, it's going to consider it signed. You get what I'm saying? When it calculates the V, it's going to consider it signed, although it is unsigned. Because signed or unsigned is left to you in your program. But the hardware is going to give you the two answers. You get what I'm saying? Anyway. So let's have more examples. For example, I have this one, guys, here. Look, same thing. I'm going to add bit by bit, normally addition bit by bit. There is no carry here. So number one, look at this is the answer. 0 flag should be 0 because the answer is not 0. Negative flag should be 1, or you can just copy this most significant bit here because the answer is negative. Okay, don't worry. Even if it is this number or unsigned, signed or unsigned is left to you. I'm telling you how the computer is going to calculate it. This is what you are going to get if you do this operation. Okay. Now, is there a carry? No, there is no carry. When I did the addition, there was no carry. V flag. What about the V flag? 1. Why? Because this is a positive number plus positive number. I get a negative number. Okay. Now that means if your numbers are unsigned, so it's correct. There is no overflow. The answer is correct. However, if your numbers are signed, so your numbers are false. It's not correct. And I did the conversion. When I did the conversion, as you see, guys, in case of unsigned, this one is 127 plus 1. I got 128, which is correct. In case of signed, this one is 127 plus 1. I got negative. Look here, guys. This is positive 121 plus 1. I got negative 120. The correct answer should be positive 128. However, my limit is positive 127. This is my limit. I exceeded the limit. You understand what I'm saying? Okay, let's have one more example. Just one more example. Same thing here, guys. Tomorrow, we are going to have this quiz tomorrow. So still it's the same thing. I'm going to add bit by bit, normally addition. Then there is a carry here, 1. Okay, there is a carry 1. Now let's look at zero flag. Zero, because this is the result. Again, the carry, maybe this is the fourth, fifth time I say, the carry is not part of the result, okay? Because some students put it in the result and then they calculate it wrong, okay? So the result means byte plus byte, I'm gonna get a byte. I wanna add byte plus byte, I store the result in a byte, okay? So anyway, now let's look at the negative flag. Negative flag, just to copy this bit, the most significant. Okay, the result is not negative. Okay, now let's look at carry. Is there a carry? Yes, there is a carry. Now look at the V flag. V flag should be 1 because I'm adding negative number plus negative number, I got a positive number. Now, what this means? So you have overflow in both cases. So if your number signed or unsigned, you have overflow. So this result is wrong in the two cases. Let's prove it. To prove it, as you see here, guys, I'm gonna add 172. This one is 172. This one is 138, and then I got 54. You got what I'm saying? For sure, it's wrong because there is overflow, right? Here, I'm gonna add negative. This one negative 84 plus negative 118. Okay, and I got 54. Okay, but yeah, this number 54 in both cases, because the correct answer was supposed to be negative 202, and my limit is negative 128. So I exceeded the limit. Okay. The last example, just quickly, I know, just last example. Okay. There's the same, everything is the same, but just last example. Yeah, let's see, for example. Okay. Anyway, so here some students were confused about subtraction. Some students told me you always do addition. What about subtraction? Okay, so subtraction is addition. It's, as I said before, addition, but you add to the two complement. So for example, I'm giving you example. I want to subtract this number from this number. Is that good? Okay, guys? So what I did addition. So I'm going to add this number to the two complement to this number. Okay. Tomorrow I'm going to give you addition. That's fine. But I just want you to understand subtraction is addition. But what I did, this number is the same like this one. Here, I'm going to get the two complement to this one. The two complement. Okay. And now it became addition. So here, I want to subtract these two numbers. So I'm going to do addition as you see it. Again, I'm just do normal addition, and this is the result I'm going to get. The zero flag should be 0 because the result is not 0. Negative flag should be 0 because the result is positive. Carry flag is 1, so there is a carry. V flag. Here, you don't think about it. This is 0 and 1. So here, 1 is 0 and 1. You don't think about it because one number is positive, the other one is negative. So you don't think about it. There is no overflow. Again, if your number are unsigned, you have overflow. Signed, you don't have problem. Let's see, prove it. I'm gonna prove it now. Look here, guys. If the numbers are unsigned, okay. Something is wrong here. Sorry.
The B is the ones complement.
No, I'm going to tell you what happened. What happens here, guys, in case of subtraction, the computer is going to flip, only in case of subtraction, the computer is going to flip the carry flag. Okay. So actually here, the carry flag should be 0. Okay. Just in case of subtraction. Okay. Because I'm going to explain it later. In case of subtraction, the carry flag, we are going to call it borrow flag if you want to borrow. Okay. Borrow flag. So forget it for now. I'm going to teach it later. But just okay. What happened now? Just in case of subtraction. Okay. What happens? The result you are going to get, you are going to flip the carry flag. Why? Because the carry flag, we're going to call it borrow flag. Okay. This flag should tell you if you need to borrow. You know what I mean by borrow. I'm going to explain it later anyway. We need to borrow. Okay. In this case, here the borrow flag is 0. That means I don't need to borrow. okay, because this number is bigger than this number. Anyway, I'm gonna explain it later, so don't worry about it. Don't worry about the subtraction for now. So tomorrow I'm gonna give you addition, but also you should understand subtraction is just addition to the two statement. However, as I'm gonna explain later, carry flag is gonna be flipped because we are gonna increase of subtraction. We call it forward flag. Anyway, see you tomorrow, guys. So we almost finished. I think we finished chapter 1. So I want you, the tomorrow quiz is going to be a large quiz tomorrow, a long quiz is going to be on chapter 1. Okay. You have, it should be easy. You already have all the slides. Just understand the slide. You have the all the lectures posted online, all the lecture on YouTube. Okay. So also you can listen to the lecture. Just understand the slides and you can bring the slides and bring them to with you.
What I was asking was,
Okay.